Okay, so AP Calculus, Calculus 30L. We're talking about linear approximations today, linear approximations. And if you're following along in your textbook, Finney page 233. All right, I have a snapshot here of a graph, okay? This is a radical function, square root function. It's y equals square root of x, and I have a tangent line here on here. Now I'm going to go over to the Desmos here, which looks right like this, okay? And this is the graph right here. Now the first point, the first concept that I want to introduce to you is this. The concept of being locally linear, okay? So in your textbook you'll see this, this paragraph. So when we're talking about linear approximations, what we're trying to do is we're trying to approximate values for a function using the tangent line to a known point. So it's kind of like we are estimating a value for a calculation of some sort, but we're not going to just use the calculator to punch it up and get a decimal answer. We're going to use calculus to do this. Okay? So what we're doing is we're exploring the relationship between estimation and calculus in terms of the tangent line and the slope of a tangent line. So the first concept is this. And I'll just kind of read this from your textbook. In our study of the derivative, we have frequently referred to the tangent line to the curve at a point. What makes the tangent line so important mathematically is that it provides a useful representation of the curve itself if we stay close enough to the point of tangency. We say that differentiable curves are always locally linear. In fact, that can be best to be appreciated geographically by zooming in to a point on a curve. Now, I have this up in Desmos, and I'm going to do that for you. And so here's the graph, and let's take a look at a section of the graph that is clearly curved, right? This is not a straight line, clearly curved. So if we take a section of this graph, right here, you can tell that it's curved a little bit. But if I zoom in, now watch the red line on the screen. Look at the ends especially. Kind of blur your eyes and look at the ends of the graph there as I zoom in. Now, what does this begin to look like here? It looks very, very much like a perfectly straight line right now. A perfectly straight line. And this clearly was a curved part of the graph. So I am in, look at how far I'm in here. 0.6766, 0.6768. Okay, so we're talking about, what is that? 10,000th of a unit here. This is from here to here is like 10,000th of a unit. So this is really, really straight looking. Even though if I zoom back out, and I keep going back out, watch the corners of the screen there, and you'll see that they start, look at that, start to bend in. So clearly this is a curved graph. But as I zoom in, it becomes like a straight line. And remember, a differentiable function has a tangent line all the way leading up to, boom, the point of tangency. And so it is continuous. It's a smooth curve. There's no corners or cusps or gaps, right, discontinuities. And so a continuous differentiable function is always linear or like a straight line if you zoom in close enough. So I'm going to do something else here now. Okay. So I am going to light up here a tangent line. Now this is the tangent line that I showed you on the other screen. This one right here. See that? This right here. Now I am going to zoom in using Desmos. I'm going to zoom in to the point of tangency right here, the point 42. Okay? So here's the point. Now clearly the graph here is not, the tangent line is not the same as the function. The function deviates from the tangent line quite a bit over here. Not so much over here. A little bit, but not so much. But what I want you to focus on is look at this right around the point of tangency here. Do you see how the lines seem to converge? They don't touch anywhere except for this point right here. But if we zoom in, notice how, you see over here on the corners of the screen, notice how the lines begin to overlap. They begin to become almost as one. You see that? So here I am zooming in. There is literally no difference between the graph and its, look at that, the graph and its tangent line. There's virtually no difference. So this is proof that a graph is locally linear. Okay, no matter how curved it is, if you zoom in enough, it appears to be a straight line. So what we're going to do, and for example, this point right here, 4, 2, I know that point, the square root of 4 is exactly 2. I don't necessarily know what the square root of 4.019 is. If I look at a graph or I punch it into a calculator, I could get a value for that. Okay? But so now let's take a look at this point right here. Can I get that to stay? I don't know. So what does that say? 4.02 and 2.005. Okay. Now is that the tangent line or the graph? Well, let's get rid of the tangent line. Let's see what the graph says. 4.02, 2.005. Okay. Let's get rid of the graph and just have the tangent line. 4.02, 2.005. So do you see how all the way along within our screen right here, the tangent line values and the function values are virtually identical. It's the thickness of the line overlaps greatly. We know that they aren't identical because the tangent line only touches technically at one infinitesimally small point. But this is good proof that the tangent line and the graph have virtually the same values if you zoom in enough. Now if we zoom back out and I light up both of these curves again, okay, I light up both these curves. You see, look at this. Now we have a great difference. Wow. So the square root of 5 is 2.25. Let's see, that's the red graph. Sorry, the square root of 5 is 2.236. Okay? And we can see that there is a difference between the red graph and the blue graph. But in close here, there's virtually no difference at all. So that is the concept of locally linear. That is going to lead us now to linearization. So if we come back here and we look at this graph right here, we are going to use the tangent line to approximate a value on the function that is very, very close to this point of tangency. Okay? So that was just concept number 1, locally linear.